My submission served to establish a link between the cell interactions in dictyostelium discoideum as a result of the protein discoidin 1 to the cellular interactions of human cells as a result of the protein DDR1 or discoidin domain receptor kinase 1. Establishing a link between the two is important as far as model organisms go and as far as research goes, because once you have a model organism as simple as dictyostelium, a lot of the work gets cut out of using things like mice. Of course, mice are going to be necessary for testing possible knockouts and things like that later, as they have similar immune systems and genetic makeups compared to an amoeba. But finding something that can be easily worked with and manipulated is just as important, and that's what I sought to do. I became interested in this work after working with these cells, dictyostelium discoideum, for the past 7 years. I've been working in a lab at Chicago State University, and I've worked with those cells the entire time, as the lab I was working in got a grant for them in my 7th grade year, and we've been working with them ever since. I started off doing very basic projects with these cells and submitting them to the Chicago Student Science Fair, which also ended up being projects that took me to the state science fair, the IJAS Science Fair. After working with the cells for so long, I was under the influence of the professor I worked with, who often gave me the ideas for things. But in my junior and senior years, I ended up formulating my own ideas for them. And some of that came after working at University of Chicago in an integrated sciences lab in the summer of 2015, where I got the idea that maybe there was some link that we could use that would make things easier for other areas. So one of those things was integration of cells with materials. The work I did at University of Chicago was creating a material from silicon nanowire that could activate the T-cell receptors, and that was a photovoltaic silicon nanowire that was able to bind to T-cells, and when stimulated by light, they would then stimulate the cell in response, and we could manipulate the TCR. I helped actually develop that material and flesh out the project before I left working to go back to school after the summer was over. But working with that gave me the idea that for 7 years I've been working with these cells, where one of their most important traits is their cellular adhesion, which is a property of discoidin 1. When we did the project at University of Chicago, we had trouble getting the cells to actually bind to these. And if there is a protein like DDR1 that is homologous to discoidin 1, that linkage can possibly serve to be something that we could more easily bind cells to, but that will require the research that I'm doing first to be fruitful. So that's where this idea came from, to find the link, or at least establish discoidin 1 as something that needs to be looked at, or that can be used as a model for DDR1. DDR1 is overexpressed in human cancer cells and tumor cells, and if it has retained the adhesive properties throughout evolution from discoidin 1, then it's kind of obvious to see why they might be overexpressing, as they're sticking together but they shouldn't be. So finding out why that happens is what I want to do. And other than that, I've also been starting a bioinformatics part of this, where I'm trying to find the point in evolutionary history where discoidin became bound to a transmembrane domain, and therefore becoming DDR1 as it is today. In the larger context of science and biology, I feel that establishing a new model organism is important, but also the applications. I feel like with today's science, and especially as we've been taught as high schoolers, a lot of science is about finding the cure for cancer, and science often focuses too much on cancer, in my opinion, when there are other diseases like muscular dystrophy, for instance, that can use discoidin as a solution to those problems. Muscular dystrophy, with the proper binding and adhesion of cells again, can be remedied. But discoidin, whenever I present it, is often looked at as how can this help cancer? And the application to cancer is that creating some type of knockout or some type of chemical that can break down discoidin with while it's in contact with cells can break up tumors. But also looking at the applications for other things is very important to me as well. And as I mentioned earlier, people who are trying to integrate cells with some materials and need better adhesion could use something like a synthetic DDR1 maybe to help their cells more readily bind to things, and that would be pretty cool. I feel like this could be highlighted just as something that is obviously still in progress. My results so far haven't been overwhelmingly positive, but I do feel like I'm moving in a better direction to figure out why discoidin 1 works the way it does and how it might work in humans exactly, because discoidin 1 in Dicty cells is a very strange thing, as it's a soluble lectin that is packaged into endosomes and then excreted, but it's hard to find them once they're excreted, and I'm still looking to find that, and highlighting this is something that has the potential to do something big, or at least minor things that can affect other fields in big ways somehow, is perfectly fine with me. I would love to be able to say that somebody found the cure for cancer, but the basis of it was finding out that you can separate tumor cells using discoidin 1 agents that break them up. That would be great.